Hi, and welcome to Multivariable Calculus, MTH218. So in this subject, we're going to look at multivariable functions. Look at what their pictures look like, how they're going to change, how you're going to add them up, how you average them, that sort of stuff. So basically, the calculus of multivariable functions. So what are multivariable functions? Well, they're functions of more than one variable. So they're really useful to model anything to in 2 and 3D in particular, stuff we see all the time. So, for example, in the picture you can see they use full to model atmospheric pressure on the surface of the Earth. So we can look at pressure at any say, XY point in a simple way of thinking about it. And so you can see this is a weather map, and so they've joined lines together connecting everything of equal pressure. They call it isobars, and labelled a few points, highs and lows, which is the minimum and maximums of this sort of function. So apart from weather maps, one is we can work out other sorts of things, other things like the mass or charge in say 3 dimensions as well. And it's also good to realise that even the weather map, while it looks 2D, can be thought of as being on the surface of a sphere, or close to a sphere for the planet Earth. And so we want to look at these functions of more than just x, y, or 2 or 3 dimensions, but also looking at on curves and surfaces too. So we'll look at quite a few of these in his sort of subject, that sort of functions. So one of the first things we're going to look in this subject is just a whole bunch of shapes that we're going to find useful for later and interesting in their own right. So we're going to look at some curves. So they start with straight lines, but also look at other sort of curves called conics, so the next complexity. So as you can see in the pictures there, ellipses, parabolas, hyperbolas, and then just thinking a bit more broad about other more complicated curves as well. We won't just look at curves, look at sort of the idea of surfaces. So the simplest surfaces are planes, and then the next most complicated one you're probably more familiar with is spheres. And then we're going to do look at what are called the quadric surfaces, and you can see a few listed on the bottom of the video here. And trying to look at strategies for understanding them. So as soon as you get into surfaces, some of those, they start getting more complex at first glance. So we'll look at strategies for understanding them, drawing them, maybe not in 3D, but in cross sections. A bit like the weather map on the previous was looking at a contour map of a variable of two different variables. Now we want to know how multivariable functions change, and this is really looking at the idea of differentiation. And so here you can see this picture, we've got a multivariate function as a graph in 3D, or the contour map in 2D, and we want to see how it changes in different directions. So the direction how it changes is really important, and we want to work out where the direction of the steep slope or no slope is, etc. And so this is the idea of directional derivatives, very much underpinned by partial differentiation. And this sort of stuff leads to optimization, and you may have seen some of this in the earlier subjects, and we'll just sort of revise that and look at some of the other aspects of it. And then it feeds on to some of the other things we're going to do, for example, some of the more vector calculus later on. We want to see not just how differentiation of multivariate function happens, but also integration. And the way of integrating functions and multivariables is called multiple integrals. So thinking back, integration in one variable is the idea of summing up stuff, or maybe taking an average of a function. So summing up something underneath the curve ends up being the area, sort of the common way of understanding it. So in higher dimensions, integration is the same idea, just adding up stuff or taking the average of what we have there. So we might have a closed surface like the torus or donut here on the left, and you want to work out the total mass of it, for example, so just summing it up, or work out the total space it takes, the volume. So we can look at things like, as I said, volumes, masses, average values as well. So we can look at the center of mass, is the idea of an average for this torus. We can do lots of more complicated things too. So when you start getting more dimensions, you can look at how things turn around and spin. So for example, on the right, we can look at the idea of moment of inertia and other sort of physical ideas. And that's really the idea of taking a an average over all different points is how lots of these sort of things work. And so we want to look at multiple integrals. So what we'll do in this subject, we'll look at lots of different skills, work out what they are, and then look at different skills of how to approach them. And then the tap on, as I'm sort of leading to, is sort of some of the applications, thinking of what they're useful for. And just like integration in one variable has quite a few different strategies, we'll see how those sort of things develop when you've got lots of them as well. To finish the subject, we're going to look at the idea of vector calculus, and this is basically how calculus applies to vectors and vector valued functions. So basically where the input and the output, so to speak, are both vectors. So this very much applies to the idea of a vector field. So maybe we should just try to explain what they are, just to help you understand what we're heading towards by the end of the session. So one idea of a vector field, perhaps like the one on the right here, is the idea of a fluid moving from 2D, like a river, or 3D, like a gas going through a room from an air conditioner, etc. Other sort of idea of a picture of what a vector field is perhaps like a picture of a force. So you've got a magnet sitting in your desk looking at all the different forces that arise from it. So a bit like a force field is the name for it. And so it could be magnetic, like I described, or it could be the electric field generated by some parallel plates you've got, or some other circumstances. So it can be forces or movement, among other things. And so when we have this sort of idea of a vector field, we want to ask questions like, how does it change? This idea of differentiation, and how can you add them up in some sense? That's the idea of integration. And these really just extend the ideas we've dealt with earlier. So extending gradient functions we'll introduce with differentiation early on, and generalizing the idea of multiple integrals we did earlier too. So we could be able to do cool things like work out the total flow through a region, or the amount of work done by a force. You can also work at total rotation. So a bit like this picture on the right here, you can work out how much something will spin as you're going on a certain path through the solid or on top of the river, as the picture might be. And we'll look at how much things are generated or destroyed. So lots of sort of questions you can ask. And we'll do it by looking at the raw skills to do it. We'll end up heading towards the end of deleting some really powerful theorems to help out answer questions succinctly. Green's theorem, Stokes' theorem, divergence theorem are the three biggies, and the fundamental theorem of line integrals is the other one. And these sort of powerful theorems are underpinnings of being able to do lots of stuff and lead on to things like complex analysis later on, complex numbers being a vector after all. So I hope that you are looking forward to this subject. I certainly am, and all the different aspects of what we can expose and delve into. Hope to speak to you soon.